Myself and my colleague Alexandre, we are in the Petrobras Research Center here in Rio de Janeiro. Professor Nelson Ebecken is in the Federal University of Rio de Janeiro. So the motivation of this work is to improve one monitoring system that Petrobras has that is in charge of the routine sea surface observation for the early detection of oil spills, helping contingency actions. We have operation 24 hours, 7 days a week, based on the visual interpretation and GIS analysis of SAR images. We also use a lot of meteo-oceanographic in situ and from satellites, ancillary information to reduce ambiguities in the SAR interpretation. This activity is integrated with oil drift modeling, in situ verification, and geochemistry analysis when we need to discover the source of the oil patches. The activity is operational since 2002, so we have a huge data set of SAR images and ancillary data to work. So why to use SAR for oil detection on the sea surface? We use SAR because SAR provides us images with a wide swath, using ScanSAR providing a synoptic view, operation at any weather and illumination conditions, suitable spatial and temporal resolutions for the detection of most of the target that interested to us, and with an important feature that is a near real-time processing in delivery, very important when you work in oceanic areas that has very changeable environments. So if you have a wind speed of at least 3 meters per second, you have brag waves in the ocean surface, and the ocean surface will look diffuse. If you have oil or any other substance or event that could damp the sea surface, we will have a dark spot, and these are our targets that we are trying to identify in this work. So here is an example of the data set we use. Here is a RadarSat-1 image acquired in April 2002. And here is the coastline. You can see lots of the dark spots. And using the ancillary data, here we have chlorophyll A data. Here it's surface temperature. Here the wind field. It will help us to identify all these features. Here they are already segmented. So it is easier to guess that this big feature is algae bloom because it's correlated with a higher value of chlorophyll. These dark patches are low winds because are correlated with this low wind area. And these patches over here are probably related with biogenic oils floating on the surface associated with the upwelling events. Here, this feature corresponds to water with colder temperature. So our objective, our desire in this work is to summarize in a procedure, in a semi-automatic or automatic procedure, all this knowledge you use to do this integrated interpretation. So the objective is to produce, to develop a classification procedure for the automatic identification of dark spots detectable in SAR images. Many authors have investigated methods to automate the oil spill detection, and usually a 3-step approach is proposed: dark spot detection, segmentation, followed by the feature extraction, and then a classification. That is the typical OBIA approach. As oil and lookalikes have similar spectral signature, procedure based on the pixel clustering is not effective to discern them, so we need additional features. And then we follow this basic workflow where the first task was to build an example data set using all the monitoring system database. This database that is 10 years of images, in situ data coming from in situ sensors and in situ verifications, and the expert knowledge the company built inside, because all these activities done inside the company. We do not hire any company to help us to do that. So after that, we did an exploratory analysis in order to define a classification strategy. And in the following steps, we use procedures from data mining in order to produce classifiers. We do not use experts' role in cognition, for example, because we find that you need too many features, very complex rows, then we think we will have a best performance in using inducing algorithms like decision trees, neural network, and support vector machines. So the example selections, we use radar SAR data with it corresponding ancillary data. The segmentation was done using the multi-resolution approach in cognition. And for the feature extraction, you use EQ cognition and ArcGIS as well. So then in the first moment, we calculated 40 features. The main features already used in the previous work as well, original ones specific to this area in data set. So then, in this point, we have a table. We export all the data from the ArcGIS to a table. And here, it was possible with this strategy to achieve 779 samples that was divided in two main categories: oil spills or meteo-oceanographic events. Inside the oil spill category, we have 3 classes: EP activities resulting from drilling in production activities, ship releases, that is the releases from ships, illegal releases from ships, and not identifiable oil. In the second category, we find 4 classes: the biogenic oil or upwelling. It was very difficult to differentiate the two because they are a lot of association among them. Algae blooms, low wind features in brain cells. In this graphic, it's possible to see how the classes have imbalanced samples. We have much more samples, unfortunately, in this AP activity class, and in that one, biogenic oils and upwellings. So the next steps, as the exploratory analysis showed a low performance using a single classifier, we did some tests. We decided to use a classification in stage. So in the first stage, the question to be answered will be: it's an oil spill with a meteo-oceanographic phenomenon. This is the typical phase. Most of the algorithms that I saw in the literature only do this differentiation: oil spills or lookalikes. So then we find that we can go further to a second stage, trying to differentiate among these 3 types of oil spills and among these 4 types of meteo-oceanographic events. So we will need 3 classifiers. The feature selection from the 40, we selected 22 more powerful features based on the frequency and relevance in the decision tree holes. And we have different kinds of features related to the scene: spectral features, textural features, geometric, meteo-oceanographic, and location. The features in red are best for the classifier 1. Features in blue are best for the classifier 2. If features in green are best for the classifier 3. Of course, the meteo-oceanographic, as expected, the meteo-oceanographic features are best to differentiate among meteo-oceanographic phenomena. And the location of the rigs and underwater pipeline is more important to differentiate among types of oil spills. And this is very interesting information. So finally, the last step is to run the inducing algorithm. For do that, we use the data miner package of Statistica, and we use 60% of the samples for training, 20% for validation, and 20% for testing. You use a decision tree from CART, neural networks. We try different types and support machines as well, different types. Here we have a summary of the The metric used for classifier evaluation was the area under rock curve. Classification performance without meteo-oceanographic features was tested also, since meteo-oceanographic data are often not available because of the frequent cloud cover we have in the area. So the classifiers have reasonable results, most of the classifiers. The best results for all cases was achieved using support vector machines. The worst result is here, trying to classify different classes of meteo-oceanographic phenomena without meteo-oceanographic features. So this is very predictable. Here we have the errors using the best classifiers, the support machine, with and without the meteo-oceanographic feature. So in the first step, using the meteo-oceanographic feature, it's possible to differentiate among oil spills and lookalikes with an predicted error of 7%. And in the next steps, to differentiate among different kinds of 3 types of oil spills with an error of 8%. And in total, we can do all the process with an error of 15% that we find that is very reasonable. The classification of meteo-oceanographic features events without meteo-oceanographic features is really bad. So the bigger difference is noticed in this case over here. So to conclude, the classifiers were able to identify with reasonable performance 3 classes of oil spills and 4 classes of meteo-oceanographic events. The models based on support vector machine using radial-based function as kernel function presented the best results for all cases. The neural network multi-layer perceptron times also presented good results. The lack of meteo-oceanographic features causes a significant performance reduction in classification of meteo-oceanographic events, classifier 3. The classifiers could perform better with new training as long as more examples were available. The use of bagging, boosting, and ensemble methods are other options to increase the performance of the classifiers. The classifiers developed have a good potential for operational use, for sure, because they have a good result. However, it will be necessary to advance a lot in the methods of automatic spot individualization, in the methods of the first segmentation, since this task still needs a lot of human supervision to obtain useful results, because we work with too small and too big objects. It's very difficult to segment meaningful objects at the same time. Thank you.